This video presents the work with the title Revisiting Visual-Inertial Structure-from-Motion for Odometry and SLAM Initialization, done by Georgios Evangelidis and Branislav Micusik from SNAP in Vienna. The paper was published in IEEE Robotics and Automation Letters earlier this year. The Visual-Inertial Structure-from-Motion problem, referred to below as VI-SFM, is an extension of the well-known SFM problem in computer vision. Typically, there is an IMU rigidly attached to the camera that observes the scene. The principle to solve this problem is the common triangulation principle, where the observation rays from visual correspondences intersect at the scene point. However, in the visual-inertial case, the camera baseline can be replaced by the IMU baseline, which can be expressed by a kinematic equation. In the case of odometry and SLAM, VI-SFM aims to estimate the pose and the velocity of the moving body, as well as the implicit or explicit reconstruction of the 3D surrounding map, based on visual correspondences and IMU measurements. The unknown body state may be augmented with the sensor biases that change over time. It is common to decouple the state tracking from the initialization part. The state tracker uses prior estimates from past frames either in filtering or optimization pipelines. However, at the initialization stage, there is no prior knowledge. VI-SFM must be solved based only on observations, which is a challenging problem when the body is under motion. This work focuses on the initialization problem and formulates a new closed-form solution. Let us assume a calibrated rig and the case where biases do not need to be modeled. That is, we are interested in estimating the map points as well as the initial velocity v and the initial orientation of the IMU, which is modeled by the rotated gravity vector g. Note that the initial position can be arbitrarily chosen. Martinelli, in 2013, proposed a model for a closed-form solution, which then was used by several methods. Suppose a single point that is seen by 3 cameras and the visual matches have been found. In a real scenario, the observation rays, defined here by the unit vectors u, do not really intersect. If we introduce some auxiliary variables lambda that denote the distance between the point and the cameras, then the map point can be expressed at any camera coordinate system as a linear combination of the initial IMU state and the corresponding range lambda. Here, the observation set theta includes the unit vector u as well as the pre-integrated gyroscope and accelerometer data. Based on this linear dependency, Martinelli used an approximation that a point is exactly seen by a reference camera and built a linear system by combining observation rays. Such a linear system can likewise result from minimizing these 3D distances. In other words, this model eliminates the point m and estimates the lambda parameters and the initial IMU state. We propose a slightly different formulation. We keep both the point and lambdas into the game, and we build linear equations by combining the point with every observation ray. In other words, we want to find the midpoint that makes the total distance minimum. Such a formulation can be seen as an extension of the midpoint triangulation algorithm in multiview and for the visual-inertial case. It is important to note that these two minimization problems are not equivalent and provide different solutions. The equivalence holds only for the unrealistic scenario where all the observation rays really intersect at the scene point. The proposed model gives a less biased solution since it reconstructs the generator of all the observations in a more symmetric way. Let us now have a closer look at the two linear systems and see how the above slight difference can have a high impact. Assume that m different points accumulated in the vector mu are seen at n different times by a moving camera. That is, the length of the lambda vector is m times n, and the Z vector denotes the initial IMU state. At first sight, we build a larger linear system because we have 3m more unknowns. However, the matrix Q has a uniquely defined structure with a nice property. It is a semi-orthonormal matrix. This is not true for the matrix B, which has a more complicated structure that depends on how the observations are combined and on how the points are seen by the cameras. The semi-orthonormality of matrix Q means that the elimination of lambda parameters can be achieved at negligible cost, since one does not need to invert or decompose a matrix. As a result, one can directly build this system, which now has less unknowns than the one proposed by Martinelli. Moreover, the resulting matrix W' has a very specific block structure, which allows the efficient elimination of the vector mu also. Such an elimination requires the inversion of only M 3x3 matrices, which has an analytic solution. Finally, the double elimination leads to a minimal system with 6 unknowns, which can be built in a very efficient manner. Unlike the state-of-the-art solution that requires the inversion or the decomposition of a large sparse matrix, with the proposed formulation, one needs to invert a 6x6 matrix to get the IMU state and then to apply a linear mapping to get the points. As proposed by Martinelli, the constraint on gravity magnitude can be likewise enforced to the reduced system. Another advantage of the proposed formulation is the block structure of the final system and the resulting relation between the IMU state and the points. This allows the direct construction of the least square solution in a very efficient way, without using large or sparse matrices. One can show that the blocks of the final linear system can be written as a linear combination of m factors, each dependent on a single visual track. As a result, we can start from a 0 6x6 matrix and a 0 6-element vector and update them after visiting every visual track. We compared the two closed-form solvers using both synthetic and real data. The O2O and P2O names refer to the observation-to-observation pairing of Martinelli and to the proposed point-to-observation pairing scheme respectively. The results here regard synthetic data gathered by AR glasses when a person walks forwards and looks around. As seen in the velocity estimation error plots, the P2O solver is more robust to tracking error and less sensitive to short integration times. Similar results were obtained for the orientation and point reconstruction error. The better performance of the P2O solver was also confirmed by experiments with real data gathered by SNAP spectacles. The experiments included multiple initializations at different times while the wearer was moving. To evaluate the performance on real data, a Kalman filter-based VIO tracker was used as a reference baseline. Again, a more accurate initialization was achieved by the P2O solver. As mentioned, the proposed formulation leads to a very efficient solution. Given the visual tracks and the inertial data, we measured the build and solve times in a typical desktop machine. The P2O solver could initialize VIO 4 times faster. When the biases need to be modeled, the accelerometer bias is integrated in a linear way. In this case, the state vector has 9 elements and the proposed formulation leads to a solution of a 9x9 linear system. However, the integration of the gyroscope bias breaks the linearity and a nonlinear optimization is required. Such an optimization may be also required when a state tracker needs a more accurate initialization. To deal with this case, we suggest a nonlinear optimizer with the minimum number of parameters. Unlike the standard visual inertial bundle adjustment that estimates multiple states, only the initial IMU state along with the map points are refined here. In order to avoid a constrained optimization and further reduce the parameter space, the observable part of the IMU orientation is directly modeled, whereby the vector g is replaced by two scalars. These plots show the convergence of the optimizer when it is initialized by the two closed-form solvers. The P2O solver lets the optimizer start from a better point in the parameter space, thus needing less iterations to reach an acceptable error level. However, the convergence may be slower when the gyroscope bias is modeled, since more nonlinearities must be compensated. This table shows the final error achieved by the two solvers and the refiner. The results regard average velocity and gravity orientation errors over multiple initializations at different times for running and head-moving sequences. As expected, the optimizer converges at the same error level in both cases, but the proposed solver shows a much lower error than the state-of-the-art solver. In summary, we propose a new formulation that leads to a very efficient closed-form solution for VIO and SLAM initialization, which is faster and better than the state-of-the-art solution. Either as a standalone solver or combined with a nonlinear optimizer that further refines the initial state, it offers a significant speed-up to the initialization phase of VIO and SLAM pipelines. The proposed model can be easily integrated into any VIO and SLAM tracker. Thank you for your attention.